Hello there. In the last video we talked about a probability mass function. So a probability mass function, as we discussed, was just a function, p, that took some event, say x, that belonged to some sample space, and sent it to some number between 0 and 1 inclusive. And this function p had the property that the sum across all values x must come out to 1. And that's what we discussed to be a probability mass function. And here x is a discrete random variable. So in this video we're going to talk about a really important property of the discrete random variable with associated probability mass function p, and that is called the expected value. So the expected value of a discrete random variable is given as follows. So we're going to abbreviate this by e of x, and this is defined to be equal to the sum of the products of x and their corresponding probabilities. And we're going to find out that this will be a good definition for the mean of a discrete random variable as well. So let us illustrate this with an example. So consider the probability mass function given by the table x px, where x ranges from 3 to 6, so 3, 4, 5, 6, with values 1 out of 10, 3 out of 10, 4 out of 10, and 2 out of 10. You can easily verify that this is a probability mass function. All the probabilities are between 0 and 1, and the sum is equal to 1. And let us also graph this so we can discuss a couple properties of this. So this is x, and this is going to be p of x. So the values are 3, 4, 5, 6, and we have 1 through 4 tenths. So 1 tenth, 2 tenths, 3 tenths, 4 tenths. So we have 1 tenth there, 3 tenths, 4 tenths, and 2 tenths. So if we were to extrapolate these values, it's possible that we can have some curve as so, right? So notice that the value between 3 and 6 is going to be somewhere with 4.5. So you may think that this data might be skewed to the left. So what values will the expected value come out to be? So let us calculate that. So the expected value of x, by definition, is going to be the sum of x times p of x. So this is going to be equal to 3 times its probability of 1 over 10, plus 4 times its probability, 3 out of 10, plus 5 times its probability, 4 out of 10, plus 6 times its probability, 2 out of 10. If we factor out a 1 out of 10 out of this, we can easily do the math to be 3 plus 12 plus 20 plus 12. And that's going to come out to 3 plus 12 is 15, plus 12 is 27, plus 20 is 47, so this is going to be 47 tenths, or 4.7. And this is the mean of the random variable by definition. So notice here that this middle line is going to be 4.5. We have more data on the right of this line, namely a reasonable value of the mean will be something slightly to the right of this, and 4.7 definitely matches that criteria. And also another reason why we want to define this to be the mean, recall that the mean of a frequency distribution for a population is going to be the sum of x times the function frequencies divided by the sum of its frequencies. So the sum of the frequencies is a constant, so recall that this can be rewritten as the sum of x times the function values divided by the sample size. So this value pretty much is similar to the probability of that value x. So one may realize why we will define this to be the mean of a random variable x. So let's look at another example. So example 2. So let x be the random variable associated with rolling 2 four-sided dice. So when I say four-sided dice, I'm assuming that you can have 1, 2, 3, or 4 as your values. So if this is my random variable x, my minimum value that I can have is going to be 2. That's going to be associated with event 1, 1. I can have 3. You can get that via 1, 2, and 2, 1. And you can go all the way down to 8 because that's going to be achieved by 4, 4. So let's calculate the corresponding probabilities. So notice here that since this is a four-sided die, the sum of the sample space is going to be equal to 4 times 4, or 16. So this first event is going to have a probability of 1 over 16, same with 8. 3 is going to have a probability of 2 over 16, same with 7. And recall for that the sum of the probabilities or the sum of the dice usually take a triangular distribution. So one can find that this is going to be 3/16, 3/16, and finally 4/16 located at 5. So if I were to actually graph this with the x values here and the p values on the vertical axis, one can see that if this is 2, 3, 4, 5, 6, 7, 8, if I were to ask you what do you think is a reasonable value for the mean of this random variable, well, you're like, okay, well, 2 plus 8 is going to be 10, 10 divided by 2 is going to be 5, and this data seems to be symmetric, so we may think that mu of x is equal to 5. So let's verify and see if that definition of expected value actually satisfies this criteria. So again, the expected value of x is going to be equal to the sum of x times their corresponding probability values. So this is going to be equal to 2 times this probability, 1 over 16, plus 3 times this probability, 2 over 16, plus 4 times this probability, 3 over 16, plus 5 times this probability of 4 over 16, plus 6 times this probability of 3/16, plus 7 times this probability of 2 over 16, and finally 8 times this probability of 1 over 16. To add this quickly, we can factor out a 1 over 16th out of everything, and we're left with 2 times 1 is 2, 3 times 2 is 6, 4 times 3 is 12, 5 times 4 is 20, 6 times 3 is 18, 7 times 2 is 14, and 8 times 1 is 8. So what is this going to come out to? Well, 2 plus 6 plus 12 is going to be 20. We have a 20 there. And what do we have here? So 18 plus 14 is going to be 32, and 32 plus 8 is going to be 40. So this is going to come out to 80 divided by 16, and that, of course, is equal to 5. So therefore what? That means the expected value of the random variable is going to be equal to 5. That is, if we roll a bunch of dice, like 5 million per se, and we take the average of all those values, then we're going to be expected to have an average of about equal to 5. And again, we sometimes write that the mean of the expected random variable x is going to be equal to 5 as well. These notations are usually interchangeable. So let's briefly summarize what we have discussed here. So consider a discrete random variable. So random variable x with probability mass function p of x. Then the expected value of that random variable is equal to the sum of the products of those values times their corresponding probabilities. And that's how you calculate the expected value, and also sometimes we denote the expected value as the mean of that random variable. And that's a quick summary of how to calculate and interpret the expected value of a discrete random variable.